Hello everyone. Today we will study a problem which relates with a well-known theorem from differential calculus. This is the mean value theorem. So as you can see, this question asks us the following. So we consider f to be a real function, and we know that it has n plus 1 derivatives at each point of the real numbers. So we have to show that for each pair of real numbers a and b such that a is less than b, then and also that fulfills the following condition, that the natural logarithm of the division of fb plus f prime b plus plus the nth derivative of f evaluated in b divided by a similar expression, but instead of b use a, is equal to b minus a. So given that conditions, then there is a number c in the open interval a and b, a to b, for which the n plus 1 derivative evaluated in c is equal to the function evaluated in c. And know that ln denotes the natural logarithm as I pointed before. Okay, so at first, as I said in the principle, we will attack this problem using a well-known theorem from differential calculus. That theorem is the mean value theorem. So what does it say, the mean value theorem? So it says the following. So just recall some parts. The mean value theorem. So mean value theorem says that, okay, we will suppose that we have a function that has a first derivative is continuous. So f belongs to c and 1. So it says that for a less than b, there exists c that belong to a to b such that f evaluated in b minus f evaluated in a is divided by b minus a is equal to the derivative of the function evaluated in c. So this is the mean value theorem. It makes sense when we consider, for example, let's say we have a function which has first derivative well defined, and this is a and this is b. And if you make the second line which join the points, then you will see that exists at least one point which has the same slope. In this case, there are 2 points, but this is this case. Yes, so at least the theorem, the mean value theorem, asserts that at least exists one value. In this case, we have 2 values, but it depends on the function too. So how can we use this theorem in our case? So let me copy this condition. This condition is fundamental, and we will see how to transform it to the hypothesis of the mean value theorem. So how can we do that? Okay, well, for obtaining this, we have to recall the properties of natural logarithm. So it means that this quotient can be transformed in a difference. It means natural logarithm of fb plus f prime b plus, okay, so we will just transform it in a difference minus natural logarithm, and the same, but instead of b we will put a, f prime a f n evaluated in a divided by b minus a. It must be equal to 1. Okay, I need some space here. This is not so important, but we will put the space. Okay, what is the main point here? The main point here is that we could transform this form to somewhat similar to the mean value theorem hypothesis. The result, sorry, from here. So Then how can we obtain similar form? So let's define a function. Which function? I will define function, I will call it g. So gx is equal to natural logarithm of fx plus f prime x plus f the nth derivative of f in x. Okay, now with this in mind, we can see that this equality in blue can be written as gb minus j is equal to b minus a, and this is equal to 1. But we know by the mean value theorem. And why we know this? Because if we find the derivative of gx, we will find that this derivative is just equal to, remember that the derivative of, here I will put a small thing to remember, the derivative of the natural logarithm of u is u prime divided by u. So u prime is the derivative of the argument of the natural logarithm function. In this case, the derivative is f prime x plus f second derivative of x, and n becomes n plus 1 because this is the following derivative to n, and the denominator is the same that the argument as shown here, so it doesn't change. So if f prime x plus f n x. Okay, now we can use the mean value theorem here, specifically here. So remember two things. We said from the beginning, what we say from the beginning? We say from the beginning that the function fx has n plus 1 derivatives. Yes? So it means that this derivative is well defined, g prime x. Why? Because all the terms that are implied, f prime x to the n plus 1 derivative of f evaluated in x, are well defined, they are continuous, and in principle we have no problems of we have no problems. We will suppose that the function will never be 0 in this, and we won't have such problems. Okay, this is like a small thing we can consider. It does not need to be strict. It's okay, but okay, we can suppose that the denominator won't be a problem, and it makes sense because b is not equal to a. So, and the denominator, remember that the denominator, g to b minus ga divided b minus a is equal to 1, so it doesn't have problems, and b is different from a. And we know that gx is a function that it has derivative. We have shown that the derivative is well-defined and it belongs to continuous functions. We don't know if the n plus 2 derivative exists, and it doesn't matter because we only require that the derivative is a continuous function too. So okay, we are until here we have no problem, and then we use the hypothesis of the mean value theorem. The main result is, we have used the hypothesis, now the main result is that there exists a value c that belongs to the open interval a to b, such that the derivative of f evaluated in this point is equal to the quotient obtained. So if we use the same here, then there exists c, and we can say here for some c that belongs to a to b. Okay, now we know that if we want to go further, then we can say that this specific case has a point c for which the derivative is equal to 1. Okay, now we can just replace. Here we have the expression for the derivative, so we just replace. So f prime c plus second derivative evaluated in c. What here is I am not doing anything that we didn't expect because we are just replacing. Now we have this function well defined equal to 1, and we only require to do some algebra. So we pass the denominator to the other side, then we will have this plus n plus 1 in c is equal to fc plus f prime c plus f n c. Okay, so first the derivative first is eliminated with the first from here. The dots, remember that it means that we will have a function without derivative, first derivative, second derivative, third derivative, fourth derivative, until n plus 1. So the first disappear with first, second will disappear with the second from the dots, and the n derivative will be reduced or will be cancelled, but one term of the left hand side, because here we have from the second to n plus 1, then we have to go for n and then it will eliminate, and we will have finally that f, the derivative of f n plus 1 derivative evaluated in c is equal to fc for some c that belongs to a to b, and this is what we wanted to prove. So finally, remember, we wanted to prove that there exists a number in C. We don't know which number, but it's okay. We are talking about general kind of functions, but at least we know that for these general kind of functions, there exists a value C for which the n plus 1 derivative of f in C is equal to the function evaluated in C. And this is the final of this problem, that this is a problem of existence using the mean value theorem for solving it. So thank you so much for watching. If you have any questions or you want to show an alternative form to solve this problem, please use the comment box. And if you want to know more about integral calculus or other branch of mathematics that we are studying and we are uploading videos, then please subscribe my channel and check the playlist, and you will find more information that you will enjoy if you like solving these mathematical problems that, as you can see, seems hard from beginning, some hard, but if you use some mathematics, if these mathematics are usually learned the first year at university, then you can see it can be solved. Also, this was a problem that was taken from the international mathematical competition held in Bulgaria in the 1994. It was due in July 30 of 1994. It was problem 3 of the day 2, so it's a problem from International Math Olympiad. So you could see even an International Math Olympiad can be solved with simple arguments. So please keep studying these kind of problems. They help a lot when you will apply to universities or make like master or PhD examinations where you will have to tackle such kind of problems. And this is a good preparation for now to be open to solve them. So thank you so much for watching. Have a nice day to everybody. Please don't forget to subscribe my channel. Thank you so much for watching.